Hi everyone, welcome back to another video of modeling and simulation of power system components using Simulink MATLAB. This is the second lecture covering the modeling and simulation of permanent magnet DC motors. Again, we are following the three different approaches to model and simulate shunt-connected DC motors. The first one is to use blocks diagram, and in order to do so we need to find the transfer function of the machine. The second approach is to use the built-in blocks, which represent the electrical components in Simscape library in Simulink. The third one and the final one is to use the built-in DC machine block available in the new versions of the Simulink MATLAB. The third approach is used to validate and double check the first two approaches. Now, in order to find the transfer function of a system, first we need to find the equations which describe the system, then identify the input and output variables, then take Laplace transform to those variables, assuming zero initial conditions, and then the transfer function of that system would be the ratio of the output to the input variables. As shown in figure 1, the armature circuit consists of the armature voltage, the applied voltage, and the self-resistance and inductance of the armature circuit multiplied by the armature current, in addition to back EMF or counter electromagnetic force EMF. Now this back EMF is represented by the rotating speed multiplied by a constant. This constant represents the flux produced by the permanent magnet, which is placed instead of the field windings. The same constant is used to find the electromagnetic torque by multiplying that constant with the armature current, and the electromagnetic torque related to the mechanical side of the machine presented by the inertia of the rotor and the damping coefficient associated with the mechanical rotational system of that motor or of that machine, in addition to any load torque applied to that machine. So we took Laplace transform to the early presented equations, and we've rearranged those equations in order to find the output of the machine, which is the rotating speed, in terms of the armature current and load torque. The machine parameters used in this simulation are taken from reference number 2, and it's presented here in table 1. Now, as we mentioned earlier, we follow the three different approaches. The first one is to model permanent magnet DC machine using block diagram as shown, and using Simscape components which represent electrical and mechanical components. And then we try to validate the previous two models using the DC machine block already available in Simscape. I think it's available in MATLAB versions from 2013 and above. Now the references cited in this video are shown here, and I've already started MATLAB. So we can open a new model by either writing Simulink or click on the Simulink button. Okay, so we're going to choose a blank model. Alright, so let's start building the first model by calling Simulink library. Okay, so we'll start picking up the blocks we would like to have to build the model. To transfer functions from math operations, like to have a gain and the sum block. From sinks, like to have the scoop to show the signal, which is in this case the rotating speed, and from sources a block, a constant, where we're going to set our inputs. Okay, so transfer function block is used to represent the electrical side of the machine and the mechanical side as well. So I've already saved the parameters, the machine parameters are presented in table 1 on M file. Just need to run that M file so that those parameters will be placed in the workspace, and then can just run the model. Okay, seems right. So this is the first model, or the first approach. Let's go and let's first make some room for the second one. So let's go and build the second model based on Simscape library. We'd like to have some components from electrical library. Inductor, resistor, and rotational electromechanical converter, which is the link between the electrical side and the mechanical side of the machine in a permanent magnet DC machine. Okay, so we need to have a server configuration, only one, since both electrical and mechanical sides will be linked. So we need only one. Well, I guess that's convenient. And from mechanical library, rotational motion sensor, to sense or measure the rotating speed, and ideal torque source to feed in the load torque. Inertia and rotational damper, plus mechanical rotational reference. Just clear those elements. from our way. All right. The same signal feeding the first model are being used to feed the second model in order to see if we have identical inputs. Can we have identical outputs from two different models? All right. All right, so I guess extend this window a little bit. All right, so the last thing is to start inserting the variables or defining the variables in the second model. I guess that's all. Let's run and see. If we can get the same signal. I guess we can. Now we've already tried to measure the armature current and armature current from the first on the second approach, around 0.2. It's also around 0.2 in the second model. Alright, so let's double check that both models work properly. Okay, so let's go and build the third model by using the block, the DC machine. We would like to have the graphical user interface, the DC machine block. With this block, you can simulate separately excited or self-excited DC machine or a permanent magnet DC machine, where the field winding terminals will disappear, and then we just need to set the machine parameters. Okay, so a torque constant, which is kV inertia. Alright, so and we'd like to check the help. When we read the help of that DC machine, we will find that the output of the block, the output of the machine, is a vector of 4 signals. The first one is the speed, the second one is the armature current. Alright, so we need to extract the signal, the output signal or signals, using a demixer. This demixer with 4 outputs, where the first output would be the speed and the second output would be the armature current. Now we can feed the DC machine by using a DC source. So basically any electrical source like DC voltage source, and then we can set that that source to the same value we've been using in the first 2 models, and the load torque as well. We're using the same load torque. So the speed seems similar to the previous 2 models. Speed, the armature current as well. Now in order to check that all 3 models have the same output, let's put them together. Okay, let's check. Okay, so they seems identical or very close. Let's see if we can get, yeah, I guess they are. So with this third model, we conclude the modeling and simulation of permanent magnet DC machine using 3 different approaches. We've concluded this video. So thank you very much for watching.